Okay, here we're told we have water entering a rigid sealed cylindrical tank, so water's coming in here at a steady rate of 100 liters per hour. That's a volumetric flow rate. And it forces gasoline, which is right up here, out as indicated in the drawing. So the water comes in, increases the height of the interface, and then gasoline is forced out. We're told that the gasoline has a specific gravity of 0.68. Now in thermodynamics, we don't tell you what specific gravity is. That's something that's covered in fluid mechanics, but I can define it here for you pretty easily. The definition for specific gravity, which has the symbol Sg, is just the density of the substance divided by the density of water at a particular temperature, and the temperature is typically at 4 degrees C. The reason we do that is because that density is 1,000 kilograms per cubic meter. It's a nice, easy number to work with. So the specific gravity of gas being 0.68 just means that 0.68 is equal to the density of gas divided by the density of water at 4 degrees C, which is just 1,000 kilograms per cubic meter, which means that the density of gas is now 680 kilograms per cubic meter. So specific gravity is just a ratio of the density of the liquid divided by the density of water at 4 degrees C, which is, again, this nice easy number, 1,000 kilograms per cubic meter. We're told the tank has a total volume of 1,000 liters, and what is the time rate of change of mass of gasoline contained in the tank? So we want to know how the mass of the gas in here is changing with time. All right, so let's get started on this. First thing I'm going to do is just apply a control volume around the water. This is going to be a conservation of mass kind of problem because I'm trying to find the rate of change of mass. So I'm thinking that it's going to be a conservation of mass problem. So actually what I'll do first is I'll put a control volume around the whole interior of the tank. Let's do that first. Okay, so there's the control volume I'm going to use, and I'll apply conservation of mass. It tells me the time rate of change of mass inside the control volume is equal to the rate at which mass is coming in minus the rate at which mass is going out. And the time rate of change of mass inside the control volume will be the time rate of change of mass of water in there plus the time rate of change of the mass of the gas, right, because it's consisting of both. The mass flow rate coming in is going to be just where the water is coming in right here. So let me call the volumetric flow rate of water coming in, let's call it QH2O. So the mass flow rate in will be density of water times QH2O. And then the gas coming out here, I'm going to call that just the volumetric flow rate there is Q gas. So the mass flow rate coming out is going to be the density of the gas times the Q gas. And we're going to treat the gasoline and water as both being incompressible. Since they're both liquids, the incompressible assumption is pretty reasonable. So this just looks like time rate of change of mass of water plus the time rate of change of the mass of the gas is equal to the density of water times the volumetric flow rate of water minus the density of the gas times the volumetric flow rate of the gas. And we know the mass flow rate of the volumetric flow rate of the water, that's given up here. The Q of the water is given as 100 liters per hour. Okay, so we still have some more work to do. We're trying to ultimately find the mass flow rate of the gas, but you see there's some other terms in here that we have to figure out. So one of the other things I'm going to do is let me just apply conservation of mass just to the water. So I'm going to just do this blue control volume just surrounding the water and apply conservation of mass to that. And so let me write it all out. That control volume that I'm using there is going to be a deformable one. I want the red one was fixed, but the blue one I'm going to make deformable so that it moves upward as the level of the water changes. Okay, so in that case, what's going to happen is the mass flow rate of water, or the mass flow rate out of that control volume, that blue one, is going to be 0 because the level is moving upwards with the water. So nothing's going out. The mass flow rate going in is just going to be the density of the water times the volumetric flow rate of the water. So then we see that the time rate of change of the mass in the control volume which is really just the time rate of change of mass of the water inside the bigger control volume. This expression is the same one as that. It's just how the mass inside this control volume is changing with time. So that's why I'm writing this down here. That'll just be equal to rho of the water times the volumetric flow rate of the water. So you can see then I could substitute this, expression right, into the wrong thing there. I can substitute it into this one, and you'll have a rho of the water times Q of the water on both sides. So this one will end up canceling out with that one, right? So what we're left with is, let me put it back into red, time rate of change of mass in the control volume is equal to minus rho gas times Q gas. So it's giving us a result that's not too surprising, right? The time rate of change of mass inside here is just going to be related to how much gasoline mass is leaving. We know the density of the gas. We still don't know the volumetric flow rate of the gas. Now the way we're going to find that volumetric flow rate of the gas is we're going to do another analysis on using that red control volume. And since I said that the water and gasoline are both incompressible, then what that means is the volume that's contained within here is going to remain a constant. So the volume is a constant inside the tank. Right? So the change in the volume within the control volume with respect to time is going to be 0, and that volume is the volume of the gas, how it's changing with time, and how the volume of the water is changing with time. Right? So this is kind of related to conservation of mass, but I'm just saying that since we've assumed the water and gasoline are incompressible, that the total volume contained within that control volume remains a constant as well, which is this. So that means that if I convert these over to, well, let me do some rearranging here. Okay, so I'm just rewriting that equation, and if I look at my expression right up here, for example, from conservation of mass applied to the blue control volume, which is just the water, I could have also written this in the following way. Oops. Okay, so all I'm doing is expanding my expression for conservation of mass for the water, just expanding out the mass being the density of the water times the volume of the water. And of course the water density is a constant. So, and then I'll have this density cancel out with that density. So in the end, the time rate of change of the water inside the control volume is equal to the volumetric flow rate of the water coming in. So this expression can then be written as just QH2O. Right? Hopefully that makes sense. So, and then the last thing I can do is do another control volume surrounding just the gas part. Let me do that. So I'll use a green control volume surrounding just the gas, and I'll apply conservation of mass to that. There may be a faster way to do all this. But anyway, this is the route that I chose. So if you do conservation of mass to that green control volume, then the time rate of change of mass inside that control volume is just the time rate of change of mass of the gas. And then there's no inlet coming in. I'm making that green one deformable so that this boundary moves up so that there's no flow into the control volume. It's just flow out, and that's given by that. So if I expand that out, I can write it this way. Right, I'm just expanding out the mass of the gas, keeping in mind that the density of the gas is a constant, so it comes outside the time integral. So the time rate of change of volume of the gas is equal to the minus of the flow rate, volumetric flow rate of the gas coming out. So this expression looks very much the same as this expression here, except for the water, the volume of the water is increasing as the flow rate comes in, and for the gas, the volume of the gasoline decreases because there's gasoline flowing out. So I can take this expression, plug it in up here, and so this becomes like that. So then we know the reason I wanted to do that is we can see then that, let me change the colors again, that the volumetric flow rate of the gas is minus the, there's a minus here and there's a minus there, so it's going to be the same as the volumetric flow rate of the water. Okay, so with that in mind, I can substitute that back in up in here. So in the end, I'm going to get the time rate of change of mass of the gas inside that control volume will be minus density of the gas times the volumetric flow rate of the water that's coming in, because I know what this value is. I know the density of the gas. We just calculated it up here. It's 680 kilograms per cubic meter. Volumetric flow rate of the water was given as 100 liters per hour. So you can do the unit conversions and work it all out, and you'll get the time rate of change of the mass of the gas as being minus 68 kilograms per hour, or minus 0.019 kilograms per second. Okay, so I kind of took a circuitous route to get here, but there may be another approach that's a little faster, but I just wanted to, well, anyway, that's just the way I did it. So, a few things in review here. First of all, just the definition of specific gravity. We won't use specific gravity much in thermodynamics, but it is used a lot in fluid mechanics. And then what we did is we did a conservation of mass analysis to the entire tank. That's a rigid control volume. So we ended up with this expression, but we needed to simplify this, or at least not just simplify, but we needed to determine what some of the parameters were in there. So what I did is I did a control volume analysis of just the water and a control volume analysis of just the gas. That's what the blue one is, gave me this, and the green one, which gave me that. And I also assumed that we were dealing with incompressible substances. I also said that the volume inside that red control volume remains constant as well. So that gave me this expression that ultimately showed me that the volumetric flow rate of the gas and the volumetric flow rate of the water are the same. That makes a lot of sense. If the gas and the water are incompressible, if I push a little bit of volume into this tank, then the equivalent volume must come out. So that's what this expression tells me, is that the volume that I'm bringing in per unit time should be equal to the volume that's going out per unit time. And with that information, I could simplify my conservation of mass statement here, that was done down here, and do the calculation. Okay, so like I said, it was kind of a long way to get there, but we ended up there nevertheless. So we'll end the example there.